This video is sponsored by Brilliant. More about them later.
Hi there everyone. Today we are going to be testing some pretty futuristic propeller technology. Now normally when I'm doing prop testing, I'm testing props like this. This is a traditional FPV drone propeller, but we're not going to be looking at that today. Today we are going to be looking at something quite a bit more exciting. This is a twisted toroidal propeller, and it's a totally new propeller design that's been invented by a group of researchers at the Lincoln Laboratory at MIT. And this design promises to be more efficient and quieter than the traditional propellers that we all know about. Unfortunately, MIT haven't open sourced their toroidal propeller design. But fortunately, a couple of people on Thingiverse, Willow Eric and Striking FPV, have been working really hard on developing toroidal propeller designs specifically for FPV drones for quite some time. Now, they have designs with 2 loops like this, 3 loops and even 4 loops, and we're going to be putting them all to the test and comparing the thrust, efficiency and noise level compared to traditional FPV props at a couple of different sizes. In this video, I'm going to be taking you through the theory behind toroidal propellers, then we're going to be looking at the thrust test stand data, and finally coming to the conclusion as to whether we are all going to be flying toroidal propellers on our FPV drones in the near future. It's a lot to cover in a video, so let's not waste any more time. Let's dive right into it. Let's start with a quick explainer on the theory of toroidal propellers. So with a traditional propeller like this, when the propeller is spinning through the air, it creates high pressure underneath the propeller and low pressure on top of the propeller, and that's what creates the thrust that pulls the propeller through the air. Now, if we come to the tip, you can see that we will have high pressure air underneath the propeller, low pressure air on top, and at the tip, the high pressure air rushes around the tip to fill the low pressure void above the propeller. So if I hold the propeller like that, the air is rushing from the underside onto the top side. And that swirl actually creates a vortex. It's like a mini tornado that flows around the tip. And that vortex propagates off behind the propeller and creates noise. And it's actually one of the main ways in which propellers create noise is from these tip vortices. What a toroidal propeller aims to do is to remove the possibility for that vortex to be formed. So same with a toroidal propeller, we're going to have low pressure on top of the prop, high pressure underneath. But when we get to the tip, we don't have a sort of easy path for the high pressure air to rush round and fill in the low pressure side. Instead, we have this sort of twisted propeller shape here with some height to it that helps keep those 2 pieces of air, the low pressure air on top and the high pressure air underneath, apart from each other. And that means that vortices do get shed from a toroidal propeller, but they don't all happen in one place at the tip. You get vortices shed evenly across the whole aerofoil profile. And because those vortices are spread out across the propeller, they're smaller, they dissipate more quickly, and they generate less noise. Also, those vortices being smaller and weaker means less energy is being taken out of the propeller, and that means that these propellers should be more efficient, generating more thrust for less drag and less power. One of the challenges with testing toroidal props has been manufacturing them. This is a traditional FPV prop, and you can see that it has a smooth and shiny surface finish. And that's because it's been manufactured by injection molding into a polished mold. Now, we don't have molds for toroidal props yet. They're just too new. So all the testing so far has been done using 3D printed props. And this is okay, but if we use a typical FDM printing process, you can see that we don't get a smooth surface. We get this sort of layered, textured surface as the part is built up layer by the printer. And this puts a 3D printed prop at a big disadvantage compared to an injection molded prop, because that smooth surface finish is going to reduce drag, it's going to improve the performance of the propeller. To try and mitigate this, I've had these props manufactured using an SLA printing process. So that's where you use a laser to cure a liquid resin to form the plastic part. And this produces a smooth surface finish, similar to what you get from injection molding, and it also allows you to form these really thin geometries which you need for an efficient propeller. So hopefully these props are going to be pretty comparable to an injection molded prop in terms of smoothness and therefore efficiency and performance. The first thing I noticed when testing toroidal propellers is how they sound. Toroidal props sound nothing like traditional props. Let's listen to a traditional propeller followed by a bunch of different toroidal propellers so that you can hear the difference in how they all sound. So what did you think? For me, the traditional FPV prop made this very characteristic buzzsaw-like tone where you've got this very raw sound at frequencies that are very noticeable. They carry well and the human ear is pretty sensitive to those frequencies. In comparison, the toroidal prop made much more of this sort of whooshing noise. Sounds like wind blowing through trees, but that kind of broadband whoosh is a lot less noticeable, to my ear at least. The frequencies there's a much wider range of frequencies, and the frequencies tend to be ones that the ear is maybe less sensitive to. And I can imagine that if you're far away from the drone, that kind of whooshing noise would blend into the natural background sound that's in the environment anyway. As well as recording the sound of the props during the test, I also measured their sound pressure level using a decibel meter. And what I found is that toroidal props are very similar in terms of sound pressure level to traditional props. They're not that much quieter. It must be the characteristic of the sound is just less noticeable to the human ear and easier to ignore, particularly when it's a bit quieter and further away. For reference, I recorded the sound with the microphone 1 meter away from the propeller during the test and 30 degrees off axis of the thrust column. Improvements in noise performance are all well and good, but I'm more interested in the performance of these props. Are they more efficient and more powerful than traditional propellers? Well, fortunately, we have all the data to make that determination from the thrust stand testing. If you want to check out this test data for yourself, I'm going to upload it all to aosrc.com under AOS Labs. And if you've not visited the site in a while, it's a great time to take a look because I've just finished updating all of the frame pages with exploded diagrams and outline drawings to help you with your build, alongside recommended parts lists and of course all of the test data on motors, props and FPV video systems that I've done so far. I'll put a link down in the video description if you want to check that out. Let's start by looking at a chart of thrust versus throttle, because I think that gives the best idea of how these props feel and also how they're going to perform in terms of power and top speed on a quad. And what we can see is that the striking FPV 3-loop toroidal prop and the iFlight Nazgul F5 traditional prop perform pretty similarly in terms of thrust versus throttle, and they both produce quite a bit more thrust than the Willow Eric props, with the 2-loop Willow Eric producing more thrust than the 3 or 4-loop version. And I think this speaks to the different priorities of the designers here. We can see that Striking FPV has clearly focused on matching the performance of a traditional 3-bladed prop, whereas I think Willow has probably focused more on noise performance than the outright aerodynamic performance of the prop from a thrust perspective. The second chart we're going to look at is an efficiency chart, and here we're looking at the grams of thrust produced by the prop per watt of mechanical power input from the motor. And the reason that we're using mechanical power rather than electrical power is that it removes the effect of motor efficiency. So we're just looking at the efficiency of the prop in this chart. And what we can see is the iFlight Nazgul F5 prop is significantly more efficient than any of the toroidal props. It produces more thrust per watt of mechanical power. And I don't think that's surprising. Traditional props like the F5 have had a lot longer to be optimized for efficiency. And toroidal props are still very new, and so we should expect them to lag behind traditional props in terms of efficiency, at least for now. Looking at the toroidal props, we can see that the striking FPV 3-loop prop is significantly more efficient than any of the willow props, and the willow props, the 2-loop, 3-loop and 4-loop design, are less efficient with more loops, and that's as we would expect for traditional props as well. The more blades or loops that a prop has, the less efficient we would expect it to be, because each of the loops interferes with the other loops on the prop disc and slightly reduces their efficiency, because each blade has to pass through the wake of the blades in front of it. The final thing to consider before I give you my conclusions is the weight of these props. The weight of a prop, particularly for a drone, is really important because a lighter weight prop can change RPM more quickly, can change its thrust level more quickly, and that helps make the drone more stable in flight. It allows the flight controller to be able to control the drone more effectively. And what we can see here is that toroidal props appear to be significantly heavier than a comparable traditional prop. And I think that's to be expected. We have that loop design, which means that effectively we have 2 blades for each loop, and so that does add some weight. The striking FPV 3-loop design is the heaviest at almost 7 grams. It's about 70% heavier than the iFlight Nowschool F5 traditional prop. And the Willow Eric props are a little bit lighter, but again, the weight increases with the number of loops. So the 2-loop prop is coming in around 4.6 grams, and then moving up to the 4-loop prop, which is again almost 7 grams. So you are making that trade-off, I think, with toroidal props. They are going to end up being a little bit heavier for the same sort of performance. And that brings us to the conclusions section of this video. So what do you think? Do you think that we're all going to be flying toroidal props in the future? Or do you think the traditional prop is still the one to beat? Well, let me give you my thoughts on it. I think that toroidal props like this are going to become a part of drone flying and FPV in the future, but I don't think they're going to completely replace traditional props. Toroidal props offer some significant advantages in terms of noise over traditional props, and we can see that already from this testing. If you're in a situation where you need your drone to not be that noticeable by people, you don't want to impact people, you want to keep the noise level down, then toroidal props offer a really amazing way to do that. Although they don't make the drone that much quieter, they do make the drone less noticeable, and the noise they make is definitely less disruptive. However, at the moment at least, toroidal props don't offer the same level of performance that traditional props do. They're not as efficient as traditional props, and they don't seem necessarily to offer as much thrust in all cases, and it does of course depend on the design of the prop. But a traditional prop is lighter than a toroidal prop, it's more efficient, and it produces as much if not more thrust. So if you're looking for maximum performance and you're not so worried about noise, for example you're flying FPV in a bando and there's no one else around, then I think you're still going to be reaching for the traditional prop for a little while longer. And unless toroidal props can overcome the weight penalty for having this double loop design, then I think that there will always be a place for traditional props where the responsiveness of the motor is key to keeping the drone super stable. So those are my thoughts. I'd love to know what you think of this toroidal prop testing. Leave a note down in the comments. And now I'm going to leave you with a word from the sponsor of this video, Brilliant. Brilliant.org is a great way to learn maths, science and computer science skills interactively. They have thousands of lessons ranging from foundational maths all the way up to advanced topics like quantum theory, neural networks and data science, with new ones being added every month. Getting started is super simple. You'll be asked a couple of questions to gauge your comfort level, and then you can dive right in. You'll learn by answering questions and figuring things out, with Brilliant's explanations and guidance to support you every step of the way. We all learn best when we're challenged, so you might not know the answers to every question. If you get stuck, Brilliant has step-by-step explanations for every problem, so you won't be stuck for long. To try everything Brilliant has to offer free for a full 30 days, visit brilliant.org/Chris Rosser or click on the link in the video description. The first 200 of you will also receive 20% off an annual subscription to Brilliant. Thank you again to Brilliant for sponsoring this video. I hope you enjoyed this video. If you did, please hit that like button and consider subscribing to the channel. That's all I'd have for you for today. So until next time, I wish you all very, very happy flying.